Thanks everybody for coming tonight. Hopefully I can teach you a little bit about what is WebAssembly and our experience at DevCycle using WebAssembly in a pretty different use case for WebAssembly than you'd normally expect. So DevCycle, what do we do? We're a feature flagging platform. So who out there has used feature flags in your code before? Cool, a decent number of you. So the gist of what a feature flag is it allows you to dynamically control parts of your code and release features to your customers dynamically. So you can basically wrap parts of your features or your functionality in feature flags, in dynamic variables, and only deploy those chunks of your code to a subset of your users. So say like a beta test group, internal testing groups. You can roll it out to specific like geographies or certain types of users. So that's generally what a feature flag, there's obviously a ton I could go into there, but that's what a feature flag platform is. We're making decisions on your behalf of what parts of your code should be enabled for different users. So obviously that means for us as a feature flagging platform, we need to support like our customers across wherever they write code or wherever they're building their applications. So whether that's on the client side with like web applications and mobile applications, or on the server side with like all the various server-side languages there are to build out APIs these days. And for us, we really split those into two camps. We have client-side SDKs and server SDKs. And so for client-side SDKs, you can think of that in like a single user context. So there's only one user that's using your mobile app or website at a time. So as a feature flagging platform, we can make an API request and get all the values for your feature flag for that individual user and serve it to that customer right when the application starts. Pretty simple. Server SDKs are more complicated because a request that's going to your API, it might be from any n number of users. Like you can't really cache that. You need in real time to make a decision about, hey, this user hit my API, what should their feature flag value be in sort of real time? You need to make that execution in real time. And so the challenge for us as like a smaller team, we have about 50 people in our company, about half of that on our engineering team, is like, how do we maintain consistency, quality, and performance across so many platforms? Like we have, I think about 12 to 14 SDKs across our client side and server SDKs, and we only have about 25 engineers, right? So like, that's a hard math problem there. So, the question when we were starting DevCycle about 2 years ago was, is there like a holy grail of cross-platform code portability we could tap into to like write a lot of this code, not all of it, but a lot of this code once and execute it across many platforms. And that's where WebAssembly comes in. So how many of you out there have heard of WebAssembly before? Cool, a bunch of you, more than I expected. So WebAssembly is a portable compilation target for programming languages. So it's a target that many programming languages, I'll get into the list of them, can compile to. It's portable, so it's a portable binary format that runs on all platforms that have a runtime to support it. So you compile your code into WebAssembly, and then no matter the architect, the CPU architecture, the OS, the platform that it's running on, the same WebAssembly package can run wherever you're trying to run. So you don't need to like build a ARM WebAssembly package or an x86. It's all sort of one compiled binary. It's fast, so it's designed to be load time efficient and executed at near native speed. So you're not going to get the same speeds as like a native like x86 like compiled LLVM package, but you'll get probably close to like as good as like a highly JIT optimized like V8 code. Oh, am I losing? There we go. A highly optimized like V8 package. You'll get similar performance. So probably like, oh, are we losing me? Okay.
No, keep going. I got you.
So yeah, so you'll get good near native execution speeds, probably like 25 to 50% slower than if it was like a native binary. It's secure, so it was designed for the web. It's a web standard, so similar to JavaScript sandboxing, we use a lot of the similar mechanisms for WebAssembly, so it's a memory-safe sandbox execution environment. it's been around, it became a web standard in 2019, started development in around 2015, so it's been around for a bit. I like to say it's neither web or assembly because it's not actually assembly code that you're compiling to, and it wasn't designed from the start actually to be only for the web. It was designed to be a portable cross-platform compilation target that targeted the web first because that's where most of the initial use cases for. And in 2019 when it launched, it officially became the 4th language of the web. Who wants to say who knows what the other 3 languages of the web are?
Sadness.
What?
Sadness.
Sadness? No, not sadness. There's 3 other languages, official languages of the web. I know you're a web developer. HTML, CSS, yeah. JavaScript, yeah. And so WebAssembly is officially the 4th. Languages that compile to WebAssembly, it's most of them, like to be frankly, I won't go through the full list here, but the languages that support WebAssembly the best are the more lower level languages, so things like Rust and C++ are probably the best targets for WebAssembly. You can do Go and C# and Swift and CPython and Java and other languages that can compile to WebAssembly, but frankly, the best support is in those lower level languages. And there's also WebAssembly specific languages like AssemblyScript, which we'll be talking about today, which is a TypeScript-like language that compiles to WebAssembly, and we'll be getting into that right here. Where can I run WebAssembly? Obviously, all major web browsers run WebAssembly. Major applications like Figma and 1Password rely on WebAssembly as their core, the core business logic. So, like when you're working on a Figma design, all the layout information is done in sort of a WebAssembly engine on your browser. 1Password uses it for all their security, authentication, crypto stuff. They're basically how a WebAssembly runtime works, and obviously all the browsers have them built in now, is that they're compiling your WebAssembly to machine code, and they're doing that sort of JIT compilation at runtime for you. There's lots of runtimes to choose from. Basically, all the languages that you can compile WebAssembly to also have runtimes, pretty much. And my recommendation would be to start with the WASMTime runtimes, and WASM is the short form for WebAssembly. There's lots of acronyms going on, and those are provided by the Bytecode Alliance, which is kind of the main open source alliance that's really pushing WebAssembly forward. So this is a tweet, and I'll read it out because it's kind of small, from one of the founders of Docker. And it's a pretty famous tweet in the WebAssembly community. Solomon Hykes says, if WebAssembly and WASI, and I'll explain what WASI is, existed in 2008, we wouldn't have needed to create Docker. That's how important it is. WebAssembly on the server is the future of computing. A standardized system interface was the missing link. Let's hope WASI is up to the task. So as he explained here, WASI is a standardized kind of POSIX-like a system interface for using WebAssembly on the server. And so that means you can interact with things like files and clocks and sockets and all those things you would need to do on the server that obviously you don't have access to do in a web browser environment. So you kind of layer on and layer in the WASI interfaces into your WebAssembly code to make your code sort of work specifically on server applications. So for us at DevCycle, we were about, probably 6 months into the product. We had built a bunch of client-side SDKs for our feature flagging platform, and we had a common TypeScript library that we were using across our Cloudflare workers and our Node.js SDK to basically make the decisions about what values a feature flag should get. So it's kind of like the core business logic library of our whole platform. And we wanted to make this, use WebAssembly to make this cross-platform. So for us, the obvious answer was to try to play with AssemblyScript. It is a TypeScript-like syntax using .ts files, using the TypeScript compiler that compiles to WebAssembly, which is pretty cool. And what it does, it'll generate automatic, it'll obviously compile your TypeScript-like code to a WebAssembly binary, and then create automatic JavaScript bindings around that. So you can basically create a module, create an assembly script module that looks just like a regular TypeScript module that you can then import or require into like a Node.js or web application, and it kind of just works as any other JavaScript module would work, which is like pretty magic. For us, this was really cool because we had this was like our core business logic of our whole product. So we had a lot of unit tests built around this code base. So we're really easily able to just like import the new library and run all of our existing tests against it and like make sure it works. So that was like a super big win. I think we did all this work over a hackathon week and got it working in like 3 or 4 days, the initial version, which was super cool. So it seemed like a really big win. So some of the challenges in how assembly script is not TypeScript is that it uses low-level types, so like floats and integers and I64s, F64s, like WTF16 strings. I could probably do a whole talk on how WTF16 strings are dumb, but there's a lot of challenges of converting between UTF-16 strings and UTF-8 strings and different runtime incompatibilities that we ran into, but I won't bore you all on that. Closures. So as you can see in some of these code examples, probably some of you can't see, but you can do closures, but you can't capture local variables. So if you have like a local variable that you're accessing in your closure, not supported in assembly script. So generally you'll have to like revert to like normal for loops and maybe some global state to do the same things. There's no promises support or async await, so tier for all of you TypeScript developers who love that stuff like I do. Yeah, you basically only have basic iterators. You have no try catch. You can only throw errors, and those errors get thrown to the stack that then need to get handled by the native code. So yeah, like throwing errors and try catching is very different. There's no native JSON or regex support, which is a real challenge. There are open source libraries in AssemblyScript, but you can imagine like JavaScript ecosystem is pretty big, but most like JavaScript libraries are only maintained by like one person, right? Like that's the reality. And it's kind of worse for AssemblyScript. You're lucky if there's a maintainer for a lot of the open source packages out there. So for all of the packages we did end up using, we had to sort of become experts in them, and we ended up having to fix like memory leaks and code bugs and string interpolation issues and a bunch of issues that we found. So yeah, we basically, for our code, had to basically rewrite it all ourselves to build out this package. So don't expect the kind of plug-and-play packages you'd get in other languages with AssemblyScript. So how to make your WebAssembly packages really slow. You have to think about interfacing with WebAssembly a bit different than native modules. So it's best to think of WebAssembly as like an external plugin system to your code. Primitive types are passed by value, but most types are copied. So passing complex data sets from your native code to the WebAssembly code is super expensive. So for example, like in our initial case, we were passing a ton of data between our native code and our WebAssembly code. You can imagine this is kind of like the workflow it would have to go through. Like you JSON serialize on the native code, you allocate a buffer to like write that JSON buffer to, then the WebAssembly has to parse that data, you have to run your logic, the WebAssembly will like serialize the output, create another buffer allocation, and then then the native code has to parse that result, right? When you think about that in your head, you're like, oh, that's a lot of work. And in our case, when we profiled it, like 80+% of our time was just passing data around, which was kind of insane. So you really need to think about how you architect your data, try to use low-level types as much as possible, avoid using JSON, use things like protobuf or Captain Proto or other sort of better transport protocols. If there's static data, you don't need to like pass into a function every time. Like pass it in at one time as sort of static data and reference it within your WebAssembly. But yeah, passing large amounts of data is going to be very expensive. We got really good at looking at these WAT files, which are basically assembly code, to figure out and do some performance optimization on this code. So when you compile your WebAssembly, you get like a WASM file, which is like the binary file, and then they get these .wat files, which are somewhat readable, kind of assembly-like code, where we looked at this a lot to like figure out where memory allocations were happening and figuring out different code paths and stuff like that. So yeah, if you want to become an expert in .wat files, write some WebAssembly. So for us, like the core thing a feature flagging server-side SDK needs to do is like give you like the proper value for a user really quickly, right? It would be like, hey, I'm in my API code path. I want to know if this feature is enabled for this user data. It should be able to do that really quickly. 97 milliseconds is not really quickly. So that's where we started with our optimization on this. And the reality of why it was so slow gets back to some of the points I just talked about, is that we were coming from a code base where this code was powering an API where we were trying to generate every value for a user and return that as an API response. And that ended up being a pretty big payload. And so to the first sort of optimization we did to get down to around 3 milliseconds was basically just cut down the amount of data that we were returning from WebAssembly from all the variables to just one variable. And that cut us down from 97 milliseconds to about 3 milliseconds. So that tells you how expensive the JSON serialization process was. And then to get down to 71 microseconds, or 0.071 milliseconds, we basically refactored and optimized the whole code path to only generate a single value for a single variable at a time. So the code path originally had a bunch of for loops where we were iterating over every feature and variable and variation and audience in your code base to like figure out what all the variable values were for that user. And obviously we had to like change a lot of those arrays into maps and do a lot of the standard sort of work you would do to optimize that code path to only go down a single code path and just figure out what the value for this variable was. And that got us down to 71 microseconds, which we were pretty happy with. We felt like that was an acceptable amount of performance for this. But we had an interesting early customer that started using our product that was a web scale company that's serving websites for company at really high scales. They wanted to use our Go SDK in their edge CDN basically. So they had a whole suite of CDN servers around the world serving traffic for websites, and they wanted to use our feature flagging platform at that super high scale, doing many billions of flag evaluations per day. Pretty crazy scale. So we obviously worked hand in hand with them and said we'd do everything we could to try to optimize our Go SDK for them. And so we spent a bunch of time to optimize down to from 70 microseconds down to 14. And a lot of that came down to like switching to protobuf from JSON. One of the neat things we did was one of the biggest costs is allocating memory to WebAssembly. So we started using pre-allocated memory. So we created these pre-allocated memory buffers that we would reuse every time we called a WebAssembly function from the Go side. And so that was one of the like neat things that we ended up doing. You probably wouldn't do that in like 99% of cases, but this was kind of like the 0.1 percentile use case that we were trying to optimize this code for. And we spent a lot of time on like automated benchmarks and in the .wat code to try to optimize this stuff. So we had this like code that we're pretty confident about. We're like 14 microseconds in our benchmark, awesome, it's going to work for them. Why do we, when we deploy it to production, is it slower? And the two main outcomes of why it ended up being a lot slower in prod. The chart at the bottom here, we got to about the P75 percentile times of like 80 microseconds, P90 of 100 microseconds, and like initially the P99 was like close to 600 microseconds, which is like half a millisecond, which is pretty slow. The two main causes of that were threading. So assembly script and most WebAssembly is single-threaded. So Go, very highly multi-threaded environment. You put in a single-threaded thing in there, things are going to get slow. We were able to get over that pretty quickly by like putting a thread pool in our Go SDK and running multiple WebAssembly runtimes at one time, and like Go just sort of like worked across the different threads. That was resolved pretty easily. The bigger problem was garbage collection. the bane of a lot of developers who are trying to do performance optimization's existence. So memory is managed within assembly script with a very basic garbage collector that's kind of bundled in with your assembly script code. And as I explained, allocations are very, very slow, about a microsecond. And so we spent a lot of time removing allocations, and we spent a lot of time tuning our garbage collection parameters to get our P99 times down by about 3x. So we got them down to about 200 microseconds eventually just by like tuning garbage collection parameters. So yeah, garbage collection makes things slow. So we're very proud of where we got to with this code base. For all of our for most of our SDK, for all of our SDKs outside of Go, so actually for our Go SDK, we ended up eventually making a native implementation that could operate at the speeds that this customer needed, because frankly, like the WebAssembly got to a point where it was fast enough for like probably 95% of Go use cases, but for these like very highly performance sensitive cases where these folks were like measuring like function times and response times and like nanoseconds and microseconds and like really profiling every piece of code, that they needed a native Go implementation. So we eventually built that. But for all of our other SDKs, for like Node.js and .NET, Java, Ruby, Python, the WebAssembly code's been working really, really well for all of our customers in using those different SDKs, and especially for like the higher level languages. We've actually proven that like the WebAssembly code executes faster than it would if we'd written that code in Ruby or Python or a lot of these sort of like higher level languages. There's a couple really cool, like the WebAssembly ecosystem's moving quickly, and some of the really cool features that are coming to it. WASI, I think, was we talked about. Interfaces, which is an interface for server features, is becoming a standard. Garbage collection. So the garbage collection problem I talked about soon will hopefully no longer be a problem, because the underlying runtime will be able to manage the garbage collection. So instead of like the assembly script garbage collector causing problems, V8 or the Go garbage collection or like the JVM can manage the memory that the WebAssembly code is using and likely be far more efficient at it. Also threading. So if you're using Rust or C++ and compiling to WebAssembly, you can write multi-threaded code today, but we can't with assembly scripts. And then probably the most interesting development in the ecosystem is the component model. So this is kind of what the Docker founder was getting back to, is that in the future with WebAssembly and the component model, you could build, instead of building microservices that are a bunch of Docker containers that can talk to each other, you can basically build a bunch of WebAssembly modules that can all be independently scaled at the edge and can all talk to each other over WASI. And so the advantages over Docker is that you can spin up a WebAssembly module in like microseconds, like less than a millisecond, versus and the memory overhead of a WebAssembly module is just the memory you need. It can be 1 megabyte. It could be like, however, it could be a very small memory overhead, so you can fit hundreds, if not thousands, of WebAssembly runtimes like running in the space that a Docker container would be running. So in the future, you could get much better utilization of your servers if we move from sort of like Docker image-based microservice to WebAssembly microservices. So that's where the component model is getting really, really interesting. And there's a bunch of like companies out there that they're pushing that as kind of like edge computing use cases and sort of replacing Kubernetes style workloads. So yeah, if you're interested in learning more and playing around with WebAssembly long term, I would probably recommend like trying it in Rust or C++. And yeah, and we believe in the future of WebAssembly. It's been really great for our productivity and our ability as a small engineering team to support and build a bunch of SDKs. And yeah, we're going to continue to invest in it ourselves. And we'll likely be switching this assembly script code over to Rust in the next 6 to 12 months and continue to sort of invest in and learn about WebAssembly over the coming years. So yeah, that is all I had. Any questions?
So, we need to unmute this.
scared to mess with
Yeah,
it.
don't touch it. I don't know what will happen. There we go. Give it a try.
Okay.
There you go.
You talked a lot about optimization. I was wondering two things. One
Yep.
was how much of the optimization for WebAssembly would you say was just general best practices that you didn't need to worry about so much in the original code versus like they became important when porting to AssemblyScript versus how much was like specifically to AssemblyScript? And then secondly, how much was things that seem to be due more to like the youthfulness of it? Like for example, you said there's a basic garbage collector. Would you foresee a more sophisticated one being part of it in the future?
Yeah, good question. It's a mixture of all of that. Like, frankly, we were coming from a code base, like as I explained, that was structured differently. So probably we got like 1,000x improvement by just changing from a code base that was trying to generate all of your variables for your code to just like generating a single variable. And that was just like our logic that we knew we had to do. But there was a lot of things that we didn't really understand the cost of transferring data in and out of WebAssembly until we started to use it and really profiling it. So that was like a real learning when we saw that in like the CPU traces that were like, oh, we're spending all of our time just like parsing data and transferring back and forth. That was like a big eye-opening, and we sort of had to rethink a bit of how our API interface for our WebAssembly. So that was a big learning that was specific to the profiling. Yeah, and then just learning how obviously inefficient JSON can be, things like that. So yeah, there is a nature of that. I would say AssemblyScript as a product is more geared towards taking TypeScript code and potentially like really like hot paths of your TypeScript code and creating WebAssembly compiled versions of that. So for example, if you're doing like image manipulation or like very CPU intensive things on your website, you might want to create an AssemblyScript version of that that might be more efficient than running in JavaScript. Though, like, to be frank, like the V8 JIT compiler is kind of magic. Like, there's millions of man and women hours that have gone into designing that thing, and it can create incredibly optimized JIT code after you give it a couple times. But you can create more efficient versions of that code using AssemblyScript and WebAssembly. So that's where like a lot of the use cases for AssemblyScript have been more on the web side, and we were kind of trying to use it more for the server side, which they do support but isn't like their core competency. And so frankly, if we were a bigger team, we probably should have just like taken the plunge and learned some Rust and thrown a couple more developers at it rather than just like me and one other person who figured this out during a hackathon week. So that's where I would start today.
Other questions? Oh, over here in the back. Awesome.
Hi, what are some of the deterrents that you would say people have towards WebAssembly or your product, for example? What is there some security vulnerability that they would like to see patched before they start using it? Is there some sort of pitfall that they see before they adopt WebAssembly?
Yeah, good question. I think it's just people don't know about it, right? Like, it's a pretty new thing for server-side use cases, so there's naturally a lot of like skeptical questions of like, is this safe to use or whatever? Is this going to do like remote code execution? And frankly, like this, once you actually look into it, the sandbox nature of like how protected the memory is and how protected the I/O is into your WebAssembly. WebAssembly has very limited access to do anything system level. So like even all the WASI interfaces I was talking about, they're all optional and can be like have to be like enabled and disabled at the runtime. So yeah, like I would say security wise, it's much more secure to run like a WebAssembly binary than it would be like a Node.js package or something. Some of the issues we've run into is some of the runtimes on the server side are a bit immature. So for example, we've had a developer working on like making the Java WASMTime runtime better. So we spent 2 weeks like making it better support like ARM Max and better supports like older versions of glibc and stuff like that the WASMTime runtime needed. So there's stuff like that where like we're working with the open source community to try to fix some of that stuff and make it run better. But yeah, I would say in general those are kind of the biggest downsides of it right now. But it's a very exciting new paradigm that I think could bring a lot of efficiencies to backend development and like computing at the edge. So we're big users of Cloudflare workers. The same WebAssembly code that we run in our server SDKs, we run that same code in our Cloudflare workers that power all of our edge APIs. So you get that really cool synergy of like the same well-tested, battle-hardened code that you can run in multiple places, which is pretty neat.
We got a question over here, Jonathan.
How would you compare LVM IR with WebAssembly? Like, do you use some of their tools as well? Because like, I feel that there are similarities between the two.
So you're talking about LLVM sort of compiling to different architectures?
Yes, it is. It doesn't have a specific architecture.
Yeah, so the funny thing with that is that a lot of the runtimes actually use LLVM under the hood to compile the machine code. So you're compiling, say, your Rust code to WebAssembly, which is like assembly-like, but it doesn't have all the architecture like machine code architecture-specific commands. And then a lot of the runtimes use LLVM sort of to sort of JIT compile the WebAssembly code to machine code to execute, if that makes sense. So LLVM is actually used as part of WebAssembly to compile down to machine code and execute your code. So it's a similar thing. It's just like you just, instead of having to like produce a bunch of binaries for like ARM and x86 and Windows and Mac and whatever, right? You're just bundling into one sort of lowish level WebAssembly binary that then at runtime gets compiled down to like the lowest level machine code that it needs to execute.
Awesome. I know we got some questions over here. I just got one more over here.
Hi, you mentioned that the company is going to switch from WebAssembly script
Yeah.
to Rust. And I would like to ask about the reasons, because I made similar switch, but totally reversed from Rust to
Nice.
Assembly script.
Nice. Yeah, for us, it's like, as a feature flagging library, like, as you saw with the example, like, performance is so important. Like, a lot of our customers have thousands of flags throughout their code that they're evaluating. So, like, one API call might evaluate, like, 10 or 50 flags, right? So, like, every evaluation has a cost. So, for us, it's really about, like, of optimizing each evaluation. And Rust also gives us the flexibility for those more C-like SDKs that we need to support. So like we're going to need to do a C++ SDK and obviously a Rust SDK and some more like lower level SDKs where we can, with Rust, where we can build out like a C library, or we can obviously just use the Rust code in the Rust SDK to execute that more natively. So we'll likely use like the multiple architecture outputs that you can use with Rust to get better performance for those like really performance sensitive SDKs.
Hi, you mentioned about performance issue with assembly script. Did you make already some benchmarks comparing assembly script to Rust? I'm asking because from my experience that was a little bit reverse. Rust needs to check a lot of stuff, like for example, if you're borrowing variables sometimes, or if you're modifying in different thread, so it's end up in absolutely different way.
Yeah.
It slowed down.
I don't expect the Rust assembly script or the Rust WebAssembly code to be like dramatically faster or different, but there's a lot more you can do in Rust to like optimize those lower level things. Where with assembly script, you're kind of hosed by like the compiler makes a decision about how it wants to optimize this code path. Where you can structure things differently in Rust and use lower level primitives and things like that to get to that point. Like we actually found multiple compiler bugs in assembly script that we had to like fix and like work with the assembly script team to fix. So like they're basically compiling your higher level code to lower level code. It's making decisions about how to organize that. So I don't expect like our initial version of our Rust code to be that much faster, but it will be faster for like the C++ SDK and the Rust SDK and our Go SDK if we can like compile it to C libs that can be used by those SDKs. And that's sort of our main motivation.
Hey, thank you very much for the talk. That was really great. How you guys actually reduced the time taken like from 97 to almost real time. That's really commendable. So my question is, my might not be directly related to the talk, but would like to give it a try. I'm a customer of Rangle.io and from a long time. I would like to know if somebody like me, who is already a customer of Squid.io or maybe something other similar services, what could be the reasons that I or maybe other people should switch to DevCycle?
Yeah, love answering that question. Love to talk to you later about how you use Split. But yeah, so DevCycle, there's a couple things we do differently. So we organize your feature flags a bit differently. Most platforms just treat every flag in your code as just like the top level item, right? And so you go to your dashboard in like Split or LaunchDarkly and just have like hundreds of flags, and it's like at scale it gets really unorganized. And so we organize multiple flags into what we call a feature, and we sort of treat each feature as a variable. And so you can have a feature where you're like, I'm shipping this new checkout flow, and that checkout flow might have 5 different front-end variables and might have like 10 different back-end variables associated with it. And in this sort of one interface, you can see that like this team owns sort of all of these variables. This is how the variable values are getting distributed to different audience segments. You can set up multiple variations all within sort of like one feature flow. So one of the core differentiators we have is like how we organize and do that. And that also allows us to do different things with how we integrate with your developer workflows. So like how we integrate with like GitHub and Jira and a lot of your developer workflow things. We're also trying to make the developer experience of like how you create the end-to-end experience of how you create feature flags in your code, how that gets populated throughout our system, how you can see the visibility of a flag from developing the code to all the way to your alerting and monitoring system and integrations with things like Datadog and things like that. So really trying to make feature flags more visible throughout your organization, so it's obvious to everyone that like, hey, we turned this flag off and like this service started crashing, like let's tie those things together, right? And really understanding like who owns these flags, like tying in directly into the code to know that like, Raj, like you created these flags, so you're the owner of these flags, and anyone looking at it can be like, oh, like he understands how these work, right? And tying that together. So lots of stuff like that we're trying to do and trying to make a more like a better developer workflow for feature flags. And there's a lot of people I think who also are scared of like the bloat of feature flags and having it become tech debt, and we're working on those problems to like try to reduce that. And we're early days, but there's lots of folks who've gotten value out of it, and I recommend you try it out. It's free to try. Like we have a very, very generous free plan. If you're using us server side, like there's you pretty much don't need to pay. If you're using us client side, there's some costs associated with our cost there. But yeah, we try to have a very generous free plan. So take a look at it.
Awesome. So probably time for one more question. If there's anybody out there that's dying to kind of ask Jonathan something in front of everybody. Do we have any? Am I not seeing any hands? Okay, perfect. All right, so everybody, big round of applause for Jonathan.